At the Felbermayr heavy-duty port, operations were in full swing as approximately 600 tons of steel arrived by ship. These materials were designated for the installation of the third bridge crane, which would play a crucial role in supplying the blast furnace. The steel structure comprised individual components measuring up to 50 meters in length and weighing as much as 50 tons each. To ensure an efficient unloading process, both a gantry crane and a crawler crane were deployed. Once unloaded, the massive components needed to be transported to the nearby coal storage area. This was accomplished using a combination of low-bed semi-trailers and telescopic trailers. The longest sections, measuring 50 and 35 meters respectively, required the use of a self-propelled transporter. Its exceptional maneuverability and traction were essential for navigating the challenging terrain of the industrial site. Without this specialized vehicle, moving such large components within the plant premises would have been nearly impossible. The designated assembly area was located adjacent to the coal storage facility. Here, all the components were temporarily stored and gradually pre-assembled over several weeks. What made this project unique was that, for the first time, a bridge crane of this scale was fully assembled on the ground before being lifted into place. This innovative concept was developed by SteelTech, with the primary goal of significantly reducing the risks associated with high-altitude assembly work. By carrying out most of the assembly on solid ground, the safety of the workers was greatly enhanced. However, while this approach improved worker safety, it posed an enormous challenge for the lifting operation. The only way to successfully position such a large and heavy structure was to use two high-capacity cranes. For this task, a Liebherr LR1500 crawler crane and an LG 1750 lattice boom mobile crane were deployed. When fully rigged, these powerful machines had a combined lifting capacity of approximately 1,800 tons, the equivalent of around 2,000 passenger cars. The first critical phase of the lifting operation involved securing the 500-ton steel structure to both cranes and raising it approximately 20 meters off the ground. Once lifted, the next major challenge was rotating the 132-meter-long steel framework by 90 degrees in a horizontal motion. To accomplish this, the crawler crane had to carefully move a distance of 75 meters while carrying the suspended load. This maneuver required absolute synchronization between theoretical calculations and real-world execution. Any deviation could have caused the structure to sway uncontrollably, leading to potentially catastrophic consequences. To ensure stability during the operation, the ground was prepared with a specially designed gravel bed, creating an even surface for the cranes. Additionally, steel plates were used to distribute the weight optimally. Hours of meticulous calculations and the skillful execution by the crane operators ensured that every movement was carried out with precision and control. Following the successful lifting and positioning of the structure, the next step was assembling the bridge crane's running gear. While the crane bridge remained suspended at a height of approximately 20 meters, another Liebherr crawler crane lifted the 90-ton running gear and carefully positioned it with millimeter accuracy. Once in place, it was securely bolted to the structure. The final phase of the project involved the precise placement of the nearly 600-ton bridge crane onto its designated tracks. With the utmost caution and precision, the massive crane was gently lowered into position by the two giant lifting machines. This operation demonstrated that a pre-assembled bridge crane could be successfully hoisted and installed, eliminating the need for complex and hazardous assembly work at great heights. Felbermayr played a key role in the scheduled maintenance shutdown of Voestalpine's blast furnace, a critical operation that occurs only once every 14 years. Given the scale and complexity of the project, multiple mobile cranes with lifting capacities of up to 750 tons and aerial work platforms reaching 60 meters were deployed. The company provided essential equipment, including mobile cranes, forklifts, and access platforms, while also managing the transport and installation of a 180-ton container. This project required nearly all of Felbermayr's logistical expertise, from securing industrial space for manufacturing to executing complex transportation operations. One of the most intricate tasks was the transportation and installation of the scrubbers. Despite the short distance between the assembly hall and the final installation site, detailed planning was essential due to various obstacles along the route. The most significant challenge was lifting the scrubber over a bridge, which required two cranes with lifting capacities between 500 and 750 tons. This setup enabled the self-propelled transporter to move underneath the suspended load before collecting it again on the other side. The removal of the old scrubber was a similarly complex operation. Felbermayr deployed an LR 1750 crawler crane and an LTM 1500 mobile crane to handle the 34-meter-long steel structure. First, the scrubber was securely fastened and carefully rotated into a horizontal position before being loaded onto a self-propelled transporter. For installation, the new scrubber was lifted 70 meters over a pipe bridge and precisely positioned between its foundation and the transporter, requiring exceptional precision and coordination. Another critical component of the project was replacing the loading bunker at the top of the blast furnace. This task required a crawler crane with a 600-ton lifting capacity and an operational weight of 725 tons, including a 545-ton counterweight. The massive counterweight was necessary to balance the crane while lifting and installing the 60-ton bunker at a height of 90 meters, with a reach exceeding 70 meters. Beyond the lifting operations, the project also included the transport of approximately 600,000 tons of steel plates. To mitigate the impact of production downtime, 3 transport vehicles operated around the clock for the duration of the maintenance period, ensuring efficiency and continuity. Felbermayr strategically selected Linz as its base of operations due to its proximity to Voestalpine, one of Austria's largest industrial facilities. This location allowed for seamless coordination, strengthening the long-standing relationship between the two companies. Acting both as a supplier and a customer, Felbermayr leveraged its expertise to provide tailored solutions that met Voestalpine's complex needs. By early October, the project was successfully completed. Felbermayr was proud to support Voestalpine in this crucial maintenance effort, demonstrating once again its reliability and proficiency in large-scale heavy lifting and transport operations. In 2013, approximately 17,000 vehicles passed daily through the A10 near Zetterhaus, and traffic volume continued to rise. By 2017, the number had increased to 20,000 vehicles per day. To mitigate the significant impact of this heavy traffic on local residents, an ambitious environmental project was launched in 2013. The plan involved enclosing a 1,500-meter section of the A10, allowing traffic to move underground and significantly reducing noise pollution. The Austrian Highway Authority ASFINAG, in cooperation with the federal and regional governments, commissioned Felbermayr Tiefbau to carry out this large-scale infrastructure project. Work commenced in August 2013, beginning with the construction of 3 bridge structures and the widening of the highway. These initial steps were necessary to ensure continuous traffic flow in both directions toward Villach and Salzburg, while also creating passages for the Zetterhausbach stream. Existing underpasses and drainage structures had to be dismantled before further work could proceed. One of the critical preparatory measures involved stabilizing the surrounding slopes. To achieve this, around 20,000 square meters of sprayed concrete were applied, an area equivalent to 4 football fields. Additionally, 43,000 meters of anchors and 3,000 cubic meters of concrete were used to reinforce the terrain. Boreholes reaching depths of up to 15 meters were drilled to ensure stability and structural integrity. The actual tunnel enclosure construction began with the earthworks for the tunnel tube in the Villach-bound direction. During this phase, unexpected soil conditions necessitated additional shallow foundations on nearly half of the carriageway to improve ground stability. Following this, a 50-centimeter frost protection layer was applied. along with a concrete road surface. Unlike standard roads, asphalt could not be used inside the tunnels due to fire safety regulations. The tunnel tubes were constructed using an open-cut method, where concrete was poured in place using specialized formwork systems. To accelerate construction progress, two formwork systems were linked together, allowing each segment of 25 meters to be completed in a single operation. In total, 125 concrete casting sections were required for the tunnel tubes. The project utilized fire-resistant fiber-reinforced concrete, with wall thicknesses varying between 60 and 80 centimeters, particularly in the lower sections of the tunnel. The central dividing wall between the two tubes was poured in advance to streamline construction. After 2 years of intensive work, the structural framework of the first tunnel tube was completed in August 2015. By December of the same year, all necessary electrical installations had been finalized, enabling the official opening of the first tunnel tube for public traffic. The second tunnel tube followed an expedited timeline, with structural work finished in just 8 months. As the interior fit-out progressed, waterproofing was applied using specialized concrete mats, followed by an additional layer of plastic sheeting to ensure long-term durability. In February 2016, approximately 2.5 years after construction began, the backfilling process for the tunnel enclosure started. The project utilized 220,000 cubic meters of material excavated from the second tunnel tube near the Towern Tunnel. This volume equates to roughly 20,000 truckloads of earth-moving material. By March 2017, the second tunnel tube was officially opened to traffic, marking another major milestone in the project. To further minimize noise pollution for nearby residents, additional sound barriers were installed at both ends of the tunnel, each extending 400 meters. The entire project was officially completed and approved by ASFINAG in July 2017. Despite challenges posed by unpredictable weather conditions and unforeseen geological difficulties, Felbermayr successfully delivered the project on schedule. With the completion of this major infrastructure improvement, the residents of Zetterhaus regained a quieter and more livable environment, while motorists benefited from a modernized and safer tunnel system equipped with the latest safety technology. Transporting and installing massive wind turbine components using SPMTs and heavy cranes. The wind energy sector has been rapidly expanding, requiring increasingly advanced logistics and engineering solutions for the transportation and installation of massive wind turbines. In 2013 alone, Felbermayr successfully installed approximately 240 wind turbines across Europe. In Austria, wind energy adoption grew significantly, with over 20% of households being powered by wind by early 2013. By the end of the year, this figure had risen to 30%. Supporting this growth, Felbermayr installed around 80 turbines in Lower Austria and Burgenland, overcoming major logistical and technical challenges along the way. Transporting wind turbine components is a highly intricate process that involves careful planning and specialized equipment. Around 1,200 transport operations were required to deliver the various parts of the wind turbines, with shipments originating from Spain, Germany, Denmark, and Austria. The logistics planning, which took several weeks, was often affected by unforeseen transport regulation changes. One such challenge occurred when the Ratterhach Bridge over the Kiel Canal was weight-restricted, forcing the rerouting of approximately 250 loads from road transport to maritime shipping. These shipments were redirected through Rotterdam and the Rhine-Main-Danube Canal before arriving at the heavy cargo port in Linz, which served as a central storage and distribution hub for the turbine components. The transportation of wind turbine components requires specialized heavy haul equipment. SPMTs, self-propelled modular transporters, played a crucial role in moving the tower segments, nacelles, and massive generators, while telesteps trailers were employed for the turbine blades, each exceeding 50 meters in length and weighing approximately 15 tons. The tower sections were transported using specialized wind tower adapters, ensuring stability and safety during transit. Additionally, low-bed trailers were used to minimize transport height and improve maneuverability through narrow or challenging routes. At peak times, as many as 50 transport vehicles were deployed simultaneously to ensure timely deliveries to various construction sites. The efficiency of this process was critical in minimizing downtime and avoiding delays in turbine assembly. Beyond transportation, the installation of these massive turbines required a combination of human expertise and powerful machinery. Setting up a large crane at a wind farm construction site was an operation in itself, requiring more than 40 truckloads of crane components and materials. The assembly process took several days, involving over 100 individual parts. Once fully set up, these cranes had an operational weight exceeding 1,000 tons. To lift and position the massive wind turbine components, 10 high-capacity cranes, with lifting capacities of up to 1,200 tons, were in operation at multiple sites simultaneously. These cranes were responsible for hoisting the tower segments, nacelles, and rotor blades into place. Additionally, around 30 auxiliary cranes were utilized for loading, unloading, and pre-assembly work, as well as acting as support cranes for rotating and positioning the wind turbine blades during installation. Depending on wind conditions, a standard wind turbine could be fully assembled within 2 to 3 days. The installation process required precise coordination between crane operators, engineers, and ground crews. A major highlight of the project was the installation of Austria's first hybrid tower. Unlike conventional wind towers, this hybrid structure was composed of 48 massive concrete segments, which were assembled on-site to reach a height of 83 meters. To further extend the structure, a 55-meter steel tower was mounted on top, bringing the total hub height to 143 meters. The rotor blades, each 56 meters long, were pre-assembled on the ground before being lifted into place using a lattice boom crane with a 153-meter-long jib. This method, known as star assembly, allowed for the simultaneous installation of all 3 blades, reducing assembly time and ensuring structural balance. Once completed, the turbine reached a towering height of 200 meters. The fully assembled wind turbine covered a rotor area of 1,200 square meters and generated approximately 3 megawatts of electricity, enough to power more than 2,000 households annually. The successful execution of such large-scale projects reflects the growing importance of wind energy in Europe's renewable energy landscape. Currently, wind power supplies approximately 7% of Europe's total electricity consumption. By 2020, this figure is projected to increase to 18%, further solidifying wind energy as a critical component of the continent's transition to sustainable power generation. As the industry continues to expand, the demand for advanced logistics, heavy lifting solutions, and specialized transport methods like SPMTs and high-capacity cranes will continue to grow, ensuring the seamless integration of wind energy into modern infrastructure.